NVIDIA's CUDA, or Compute Unified Device Architecture, is a parallel computing platform and API that allows users to achieve accelerated computing abilities. So in this project, we're gonna get into a little bit of the background and the history, as well as a little stuff that goes under the hood, some of the hardware, and then run through a programming example that shows off what CUDA is good at. So a little bit of the history. In the early 2000s, GPUs began to develop into these specialized pieces of hardware that utilize multi-core parallel designs that were initially optimized for 3D graphics rendering, but NVIDIA realizes their potential for accelerated computing and looks for a way to make it more accessible to programmers by combining the strengths of the CPU and the GPU. Today's applications include machine learning, data science, scientific computing, accelerated encryption, and a lot of other stuff. A lot of scientific stuff, a lot of fluid rendering and graphics rendering and computational chemistry, you name it. CUDA platform also includes hundreds of libraries, compilers, and developer tools that all make it quite easy and accessible to use. Um, so a little bit about parallel computing. So CUDA is a parallel computing platform that utilizes heterogeneous computing to achieve accelerated general purpose processing. So parallel computing is all about running tasks in parallel, and it's not unique to the GPU, but it is something that the GPU is really good for. So a CPU, which is the main processor of a computer, is capable of handling really complex tasks and large instruction sets with low latency. Whereas the GPU, while it does relatively simpler tasks with smaller instruction sets, it's capable of really high throughput. So it focuses on throughput over latency. So whereas the CPU is designed for speed with complex tasks, the GPU is designed for throughput with relatively simpler tasks. Um, and heterogeneous computing is the combination of the two. So the combination of the serial computing of the GPU and the parallel computing of the GPU. And CUDA utilizes them both. Um, so some architectural similarities. They both have a control unit, an ALU, a cache, and some DRAM. And while they have many other things, these are some of the basics that are going to differentiate them in what we're talking about today. So the control unit, it's going to direct the other components within the processor, issuing instructions, scheduling tasks, controlling the movement of data. It's kind of like the brain of the CPU, whereas the ALUs are really like the workhorses, they're the tasks. So tasks are broken down into these really low-level arithmetic and logical operations that are sent to the ALUs where they're executed on. And so it really breaks it down into the most simple form of that they can be divided down into. A cache is a relatively fast and small storage system um, that the CPU utilizes to keep relevant data nearby. So it's going to really improve the latency of a CPU so that every time it needs something, it doesn't have to go all the way back to main memory, but it's got this quick access cache that's keeps only the most relevant data nearby. Um, and DRAM is main storage area of a processor, which is organized to handle large sets of data. So while we see the control, the ALU, the cache, and the DRAM here in the CPU, the GPU has much smaller control units, ALUs, a lot more ALUs, even though they're smaller, and it's also going to have memory, and it has a cache, but the cache is very limited. So some of the architectural differences here. So as we talked about the control unit on the CPU, it's quite large, quite capable of complex stuff. And the GPU is much smaller. There's a little bit more of them, and they're much simpler as far as what they can do and what they can coordinate. Um, Kind of same thing with the ALUs. So the ALUs, there's not as many of them as on the GPU, where there's going to be hundreds, if not thousands, of ALUs spread throughout cores in the GPU that all run in parallel. The ALUs of the CPU are able of handling, more complex tasks, more complex sets of instructions. So the cache in the CPU, it's going to be pretty big, and it's going to be there's multiple levels to it, and it's going to help cut down on latency. So it's going to speed everything up for the CPU. The GPU, we're not worried about that because we're worried about throughput. What we're doing is relatively simple, but we want to do a lot of it, and that's what the GPU is good for. The main memory in the CPU is highly organized and linearly accessed. So that's kind of like if you imagine accessing an array. It's much more complicated than this, but you can index straight to the array or straight to any element in the array if you have the index. Whereas the GPU, the way that memory is stored is going to be in these like large blocks of data, and it has a few different types of memory, global and shared memory, and it's going to be stored in these large blocks of data that we're going to index explicitly. So through threads and blocks and grids, which we'll all get into, but it's going to be much different than accessing memory in the CPU. So a little bit of how all of this works. We're going to talk about cores, threads, and kernels. So a core is a hardware unit in the GPU that executes instructions. It has multiple ALUs within it, and the cores are going to be coordinated throughout. So once again, these might represent something like cores throughout the GPU that all contain ALUs within them. When the ALUs do the actual arithmetic operations. Once again, much simpler than in the CPU, but there's a lot more of them. And so a good example here to kind of make sense of it is the cores are the workstations and the ALUs are the actual tools. A thread runs a kernel on a single piece of data. So a thread isn't a piece of data, but it runs a kernel on a piece of data. So it kind of combines the two. And multiple threads are mapped onto cores, but not one-to-one. So there's going to be more threads than cores, and the threads are going to be coordinating themselves from the control units through the cores. A kernel is a function that the programmer writes. So it's a relatively simple instruction compared to like a CPU function given its instruction set, but a kernel is going to be like a function within the GPU, within CUDA. And the example here is that each thread is a worker and each kernel is the worker's instructions. And so there might be a lot of workers and they might all have the same instructions, so they might have slightly different instructions. The instructions are the kernels. The workers are like the threads, the workstations are the cores, and the ALUs are like the tools. And so here we can kind of start to get an understanding of blocks and grids. If the workers, the threads, are all given the same instructions, kernels, each worker takes a turn at different workstations, cores, to execute their instructions using their tools, which are the ALUs. And these are going to be organized into blocks where all of these things are happening in parallel at all these different workstations as the threads move from one core to the next. And these are going to be arranged in these big blocks here, which are then going to be arranged in even bigger structure called a grid. Okay, so the programming model with CUDA. So we're still running a program on the CPU. Remember, we're doing heterogeneous processing. So we're using the CPU and the GPU to achieve computational throughput. So we're creating functions called kernels. We're configuring blocks and threads and explicitly managing our data throughout. So the CPU, it's important to remember that the CPU controls the workflow, the kernels run on the GPU, and the data is divided into blocks and threads. Those are kind of the main points here at this moment. So, and here's a little example of a kernel from our sample program, which we'll look at later. And it looks a lot like a function in the CPU. It doesn't look too different. We have this global keyword and we have some differences here, which we'll go over, but it's the same kind of idea. Okay, so managing data in the CPU. Once again, we have our CPU memory, which in this case in CUDA we'll call the host, and the GPU memory, which is called the device in CUDA. And memory, once again, must be explicitly managed. So we allocate memory in the device, and we use built-in functions to copy from the host to the device. So here we have we're moving some memory back and forth with this CUDA memcopy, this built-in function in this CUDA library. And here we're specifying from the host to the device. And we're passing in we're going to pass in two arrays, which we'll go over in a second, but we're passing in these two arrays from the host to the device, and then we're adding them together and we're bringing them back later. So later in the program, we go from the device back to the host so that we can look at our results. And we also need to point out that the threads are being directly indexed using these indexing methods within CUDA of thread IDX, block IDX, and block dimension, which is the index of the block, the index of the block, so the index of the thread within the block, the index of the block itself, and the threads per block. And that's going to give us our index, much like we would need an index in a for loop or a while loop or something like that. So here's a little breakdown of the flow. We have our CPU on the left and our GPU on the right. Our program starts, we allocate memory on the host and on the device. So we're going to initialize the data on the host. And you see we have our large array of data here. And we're going to copy our data to the device. So over here, our data in the device, we can think of each cell as being handled by a thread, not being a thread, but being handled by a thread. And the whole table might represent one block. Although in a if you're really utilizing CUDA, you would have many blocks. But in this case, um, we're going to just think of this as one block. And so from the CPU, we're going to launch the kernel. And then the kernel is going to be run in the GPU. So we're going to pass in the number of blocks and the threads per block as we run the kernel on the GPU itself. So each block will be scheduled onto a set of cores. And the groups of cores will process the data and then store it on the device, the GPU storage, and copy it back to the host. So we can see that whereas all these things might have happened on the CPU without CUDA, here we're passing them off to the GPU so the GPU can do what it does best, and then we're going to bring them back. And that's actually going to be way faster than just doing it on the CPU because of our architecture, because of how we're all organized together. So we're about to run this sample program, but just to kind of give an overview of it before we take a look at it, our sample program is going to add two large arrays together using the GPU, and it's going to record how long it takes to add all these elements. And then we're going to add two large elements using the CPU, but we're only going to let it execute for a similar amount of time as it took the GPU. And then we're going to compare the difference to show the speed difference. So we're going to see how many elements the CPU can add before time is up, essentially. So let's go ahead and bring in our program. So up here we see that this capital N, this is going to be the number of elements in an array. So this is over 1 million elements, quite a bit. We're also going to define our threads per block. And here we're allocating memory in the CPU right here, just like we normally would allocate a pointer. And we're going to initialize these arrays. And then we're going to allocate some memory that we're going to pass to the GPU. So this CUDA A, CUDA B, and CUDA C. So CUDA A and B are going to be arrays that have data in them, and then we're going to add them together and put them in CUDA C. And so see here we're CUDA malloc, so we're allocating space on the GPU itself here, and then we're copying from host to device, which we looked at earlier. We're passing in, this is the destination, this is where we're passing it to, this is where we're coming from, the source, and we're also explicitly saying what the size is. So it's the number of elements times the size of an integer, because our arrays are made of integers. We have to explicitly say it's not just 1 million elements, it's 1 million times the size of an integer that we're allocating or that we're storing, initializing this memory in the GPU itself. And then we're going to set up some timing. So we're going to record the amount of time, and we're going to call our kernel here. That's what our vector add is, and it looks a little different than a normal function because we're passing in the blocks here, which we initialize, and we're also passing in the threads per block, as well as our 3 are CUDA A, CUDA B, and CUDA C. And then we're going to stop the time. And yeah, so let's take a look at the kernel. So here we can see this global keyword, which is going to tell us that this is going to be an operation that's done on the GPU itself, vector add. So we're going to set our index using our indexing methods that we learned about. And then, as you can see, this is a really simple, by adding these two arrays together, it's going to do it all in just like 2 lines of code, and it's going to do it really fast. All, millions of these elements. And then after that function runs, it's going to come back and we're going to copy the memory from the device back to the host again. And then this is all this code is running it in the CPU, like I said, with the same amount of time to see how many we can get through and clocking it. And then we're going to free up our memory here at the end. So let's go ahead and run this and see what the difference is. It's all going to happen really fast. So, but the comparison is pretty stark. Okay, great. So CUDA vector additions of over 1 million took 0.7946 microseconds. So that's pretty fast. And the CPU was able to process 65,000 elements in 1 microsecond. So it had more time and it got way less elements added. So this just shows off just how much faster the GPU is than the CPU. And while even though this is a relatively simple program, the potential is pretty obvious. And the things you can do with CUDA are pretty awesome. And this is kind of just a brief glimpse into it. Great, that's going to be it. Thanks for watching.